In today's lesson, I will give you the answers of the exercise problems related to simple harmonic motion. Number 1, this figure 10.1 shows some sand placed on a flat horizontal plate which is made to oscillate with simple harmonic motion in a vertical direction. The frequency of oscillation of the plate is 13 Hz. The acceleration A is given by A equals minus omega squared times x, where omega is the angular frequency. We want to determine the angular frequency omega. We know that omega is equal to 2 pi f, so it is equal to 2 pi multiplied by 13, or you use calculator to find omega equals 81.86 or 81.7 radian per second in 3 significant figures. And then we want to determine the amplitude of oscillation of the plate such that the maximum acceleration is numerically equal to the acceleration of free fall. So A max is equal to omega squared times x0. In this case, it is the same as the acceleration of free fall, or g, which is 9.81. So 9.81 should be equal to omega squared times x0. Yeah, this is the maximum acceleration. We can find here that x0 is equal to 0.00014704 in meters. So in millimeter, we can use 3 significant figure, becomes 1.47 millimeters. What will happen to the sand on the plate in A when the amplitude of oscillation of the plate exceeds the value calculated in A2? Give a reason for your answer. Now, since the only downward force acting on the sand is their weight, and so their maximum downward acceleration is the acceleration of free fall, then when the amplitude of oscillation of the plate exceeds the value calculated in A2, then the maximum acceleration A naught of the plate will be greater than g. So when the plate is accelerating downwards from its upper maximum displacement, the sand will, of course, leave the plate. Number 2, figure 17.1 illustrates a vertical spring supporting a mass. The mass is given a vertical displacement and then released. And this figure 17.2 shows the variation with time t of the displacement y of the mass from its mean position. A student claims that the curve of figure 17.2 may be represented by the equation y equals y0 times the sine of omega t. State 2 reasons why the use of this equation is inappropriate. This equation is inappropriate because we see that the graph shows that the amplitude is reducing, so it is not constant. And the graph does not start at 0. You can see that it starts from minus 1.5. So it is not a sine wave. It should be a cosine equation. Calculate the angular frequency omega of the oscillations. We can see from the graph that the period of the oscillation is, we see the period of the oscillation. This consists of 1, 2 oscillations. 1, 2 oscillations is 1.2 seconds. So one oscillation is 0.6 seconds. So the time to do one oscillation, that's the period. It is equal to 0.6 seconds. And then the omega is equal to 2 pi over period. So 2 pi over 0.60 seconds is equal to 10.47 or 10.5 radian per second. Question C. The mass, which is a lump of plasticine, is now flattened so that its horizontal surface area is increased. The mass of the plasticine may be assumed to remain the same. It is given a displacement downwards of 1.5 centimeters and then released. Sketch a graph on figure 17.2 to show the subsequent oscillations of the plasticine. Now we can see that when the horizontal surface area is increased, then it will affect the motion because the air resistance will also larger. even though it is given the same displacement of 1.5 centimeters downwards, so the initial displacement is equal before, but then it will have smaller displacement. The next displacement will be smaller than before because of the increasing air friction. Yeah, so this is the graph of the new oscillation when the horizontal surface area is increased. Number 3, we have figure 16.1 illustrates a tube with one end sealed and some lead shot placed in it, floating vertically in a liquid of density ρ. The tube has a uniform cross-sectional area A, and the total mass of the tube and its contents is m. The tube is given a small vertical displacement and then released. The vertical acceleration A is given by minus A is the area, times rho times g over capital M times y, when g is the acceleration of free fall. Now, show that the tube is undergoing simple harmonic motion with a frequency f given by this equation, 1 over 2 pi times the square root of a rho g over m. Okay, we can see that we have this equation A equals minus a rho g over m times y. So A is proportional to y. And then this negative sign shows us the opposite direction of A. So A will be in opposite direction to y. And those are the characteristics of a simple harmonic motion. So this motion is simple harmonic. So when A equals minus omega squared times y, and we have this equation, then we can see that omega squared is equal to a rho g over m. So omega is given by the square root of a rho g over m, and omega itself is 2 pi f. So the frequency can be given by 1 over 2 pi times the square root of a rho g over m. For question B, the variation with time t of the vertical displacement y of the tube in another liquid is shown in this figure. The tube with an external diameter of 2.4 centimeters is floating in a liquid of density given 950 kg per meter cube. Using the equation in A before, determine the mass of the tube and its contents. So from the graph we can see that the period is 0.6 seconds. Yeah, period is the time to do one oscillation. So it is 0.6 seconds. And t is equal to 1 over frequency. So when frequency is 1 over 2 pi times the square root of a rho g over m, so period will be 2 pi times the square root of m over a rho g. 2 pi times the square root of m over a rho g. So t squared is equal to 4 pi squared times m over a rho g. We square both sides. So m can be given by t squared times a rho g divided by 4 pi squared. So m will be equal to 0.0384 or 0.38 kilograms in two significant figure. This a is equal to pi times r squared. The r is 1.2 centimeter and convert it into meter because we are given the diameter. Yeah, this rho is 950. Okay, that is the mass. And then write down the feature of this figure that indicates that the oscillations are damped. Of course, the decreasing amplitude indicates that the oscillations are damped. So that is the feature, the decreasing amplitude. Number 4 is from the second exercise that I gave you today. We have two vertical oscillating motions shown in figure 15.1. A ball suspended from a spring and immersed in water is shown. And then a ball bouncing on the ground is shown in this figure 15.1 II. Sketch labeled graphs to show possible variations with time of the velocity for this motion. So a possible velocity time graph for 15.1i is a lightly damped simple harmonic motion. So a lightly damped simple harmonic motion will be like this. It begins its motion downwards, and then the amplitude is getting smaller. And then this is the possible velocity time graph for the second figure here. When we assume that the air resistance is negligible, then the velocity time graph will be like this, with equal gradient. B. For the motion of the ball on the spring, describe how the direction of the acceleration varies with the direction of the velocity. When moving towards the equilibrium position, then the ball's acceleration is in the same direction as its velocity. But when it is moving away, the acceleration and the velocity are in opposite directions. That is for BI, the direction of the velocity. So we have two parts. When it is moving towards equilibrium, acceleration is the same direction as the velocity. But when it moves away, the acceleration and velocity, they are in opposite direction. For BII, the direction of the resultant force and the acceleration, of course, they are always in the same direction. Yeah. So remember here that the acceleration of an object moving in simple harmonic motion is the acceleration that brings back a particle to its equilibrium position. And the resultant force is equal to mass times that acceleration. This is called the restoring force. A restoring force is a force that brings a particle back to its original or equilibrium position. The ball on the spring is described as undergoing damped simple harmonic motion. Write down two changes which may be made to the apparatus so as to change the degree of damping. So if we want to change the degree of damping, there may be two possibilities. We can reduce the degree of damping, and we can increase the degree of damping. To reduce the degree of damping, what can we do? We can remove the water. Then it will reduce the degree of damping because we reduce the resistance. To increase the degree of damping, we have to increase the resistance. Then we need to replace the water with a more viscous fluid. For example, we change it into oil. Yeah, so those are the changes can be made so that we can change the degree of damping. The next question is we want to explain the effects within which the degree of damping have on the movement of the ball. With light damping, the ball will oscillate with gradually decreasing the amplitude. And then for critical damping, the ball returns to its equilibrium position in the shortest possible time without oscillating. And for heavy damping, the ball will take a long time to return to its equilibrium position. About this, you can see in your physics textbook on page 301, it is stated that critical damping is the minimum amount of damping required to return an oscillator to its equilibrium position without oscillating. Underdamping results in an unwanted oscillation. Overdamping will result in a slower return to equilibrium. Number 5, the variation with frequency f of the amplitude x0 of the forced oscillation of a machine is as shown in figure 18.1. Write down what is meant by a forced oscillation. A forced oscillation is an oscillation that is sustained by an applied periodic force, doing work against the dissipative forces or replacing the energy lost to dissipative forces. And state the name of the effect illustrated in figure 18.1. In your book, it is on page 301. And this is an effect called resonance with light damping. The machine's oscillations may be taken as simple harmonic at any frequency. For the machine vibrating at maximum amplitude, determine the maximum magnitudes of its linear speed. So we want to find phi max. Phi max is equal to omega times x naught, or the amplitude. Omega itself is 2 pi f naught times x naught. So 2 pi multiplied by 12 multiplied by the amplitude is 1.6 times 10 to the minus 2. The amplitude is 1.6 times 10 to the minus 2 in meter. So Vmax will be 1.21 meter per second. And the maximum magnitude of the linear acceleration, Amax, is equal to omega squared times x naught. This equation has a negative sign, but in this case we only want to find the maximum magnitude of the acceleration. So it is equal to 2 pi f naught squared times x naught. It is equal to 91 meter per second squared. Find the time interval between a maximum linear speed and the subsequent maximum linear acceleration. In this case, the variations of velocity and acceleration with time are always 1/4 cycle apart. What does it mean? When velocity is at maximum position, acceleration will be minimum. And when velocity is minimum, acceleration will be maximum. So the difference in time will be 1/4 cycle, 1/4 period. So time interval between maximum velocity and the subsequent acceleration will be 1/4t. So it is 1/4 times a period is 1/frequency. So it is equal to 1/4 times 1/12, because the frequency is 12, equals 0.02083 or 0.208 seconds in 3 significant figure. And then the mass of the machine is increased so as to reduce the maximum amplitude of the oscillations. Comment on the effect this increased mass will have on the shape of figure 18.1. If you wish, illustrate your answer on figure 18.1. So with a greater mass, the curve will be lower and flatter, and the peak would shift to a lower frequency. So you have to draw it like this. The peak will shift to a lower frequency, and then the curve will be lower, and also it will be flatter. Okay, that's all. If you have any questions, you can always ask. Thank you for your attention. I hope this video is useful.